Okay, let's dive into this explainer. When you look at an oil rig, what do you actually see? You see towering steel, massive engines, roughnecks muscling around heavy iron. Honestly, it looks like an industry built entirely on brute force. But beneath all that heavy metal and grime, the whole operation is governed by something completely invisible: strict mathematics. Today, we're looking at this invisible blueprint of math, the equations that dictate literally every movement, every single lift, and every safety mechanism on a drilling rig.
To really grasp why this math matters, you kind of have to respect the sheer, frankly terrifying scale of the physical forces we're talking about here. We're dealing with well pressures that can reach up to 15,000 pounds per square inch. We're talking about hoisting systems suspending over 1 million pounds of steel, dangling 2 miles deep into the earth. These absolutely aren't forces you can just eyeball or guess. When you're managing numbers this large, there is zero margin for error.
And that brings us to the core thesis of our explainer today. Beneath the roar of the diesel engines and the constant spin of the drill string, rig safety relies entirely on a few simple, absolutely unbreakable mathematical formulas. From Boyle's law dictating your emergency power to the geometric calculations keeping the wellbore clean, it's the math that acts as the ultimate, final barrier between order and catastrophic disaster.
Here is our structural roadmap for today. First up, pressure limits and well control. Second, hoisting and weight dynamics. Third, calculating fluid volumes. And finally, torque, output, and production.
Section 1. Pressure limits and well control. The power of squeezed gas. Think about this. If the rig loses all power and you've got a high-pressure gas bubble climbing fast to the surface, how do you slam the blowout preventer shut? Well, the answer lies in the accumulator and the math of squeezed gas. The accumulator uses nitrogen gas to squeeze hydraulic fluid, storing up emergency power. But how much power do you actually have? According to Boyle's law, which tells us that pressure and volume are inversely proportional, a gas compresses, but a liquid doesn't. So an 11-gallon accumulator bottle, pre-charged with 1,000 psi of nitrogen, does not give you 11 gallons of fluid, because the gas takes up space. It actually only gives you about 5 usable gallons. So this crucial point is summarized perfectly by this rule of thumb. A full accumulator gauge does not mean a full accumulator. A gauge reading 3,000 psi only tells you the fluid is pressurized, not how much nitrogen is pushing it. If your nitrogen slowly leaked out over time, the gauge might still read full, but you'd have zero pushing power. Trusting that gauge without physically verifying the nitrogen precharge, that is a fatal trap.
And what exactly is that accumulator fluid pushing against? The blowout preventer stack. An annular preventer is rated to hold back working well pressures of 5, 10, or even an extreme 15,000 psi. Yet, it only takes about 1,500 psi of hydraulic closing pressure to shut it. Why? It's a deliberate mathematical design. That much lower closing pressure squeezes the reinforced rubber iris shut around the pipe without over-crushing and destroying the rubber element itself. To prove this system actually works, the industry relies on the strict API 16D rule. Your accumulator must have enough calculated fluid volume to close all the pipe and shear rams, close the annular preventer, open the hydraulic choke line valve, and, here is the real kicker, still retain 200 psi above the nitrogen precharge. It's an uncompromising math test, and it proves well-controlled readiness before an emergency ever happens.
Let's move to Section 2. Hoisting and weight dynamics, mathematics of lifting. Moving up into the air, we are introducing the mathematics required to handle hundreds of thousands of pounds of steel hanging directly over an open hole. Gravity never takes a day off, and neither does the math keeping it in check. You see, rig hoisting is like a chain, and the load flows through every single link. Contrast the massive 1 million plus pound rating of a drilling rig against the 100 to 250,000 pound rating of a smaller back-end servicing unit. Everything connected to these systems, the hook, the bales, the elevators, has to match or exceed these exact tonnage classes. If you accidentally put a 150-ton bale on a 500-ton hook, that weak link immediately becomes a deadly liability.
And this brilliantly illustrates the danger of assumptions when lifting. On the rig floor, air hoists or tuggers lift the heavy tools. But look at this comparison. An air hoist stamped capacity rating literally only applies to the very first layer of rope on the drum. Because torque equals force times radius, every extra wrap of rope on that drum increases the radius, which mathematically reduces what it can safely lift. If you have 4 layers of rope spooled out, your 3,000-pound hoist might only be able to lift 2,000 pounds safely.
Let's shift and look at weight applied downward.
Weight on bit, or WLB, is the precise downward force the driller lets rest on the bit to actually crush the rock. For a roller cone bit, the sweet spot is typically 3,000 to 5,000 pounds per inch of bit diameter. And here is a real rig secret for you. Slow drilling usually means a dirty hole, not a dull bit. You absolutely must diagnose your fluid hydraulics before you simply add more weight.
Now, what's really interesting is how simple this math actually is in practice. Walk through this with me. Say you have a 12¼ inch bit. Apply that formula of 3,000 to 5,000 pounds per inch. Boom. The driller immediately knows to set the console for roughly 37,000 to 61,000 pounds of weight on bit. That specific math ensures they maximize penetration without instantly destroying a $30,000 tool.
On to Section 3, Calculating Fluid Volumes, the Hidden Geometries. When you are pushing drilling mud 2 miles deep into the earth, you obviously cannot see where it's going. You can only calculate it. So understanding the math of empty space is absolutely critical. The most important empty space on the rig is the annulus. That's the ring-shaped gap between the drill pipe and the hole itself. The math to find its volume is the hole diameter squared minus the pipe diameter squared divided by 1029.4. This gives you barrels per foot. It's a delicate balancing act. A narrower annulus means faster fluid that cleans cuttings out better, but that exact same friction puts much harder pressure on the fragile rock formation.
Let's do a quick mental check, just like a driller does right on the floor. Take our 12¼ inch hole. Square it, you get about 150. Take a 5-inch drill pipe, square it, you get 25. Subtract them to get 125. Divide that by our constant, 1029.4, and your result is about 0.12 barrels of fluid per foot.
So why does that exact 0.12 number matter so much? Because of this hard-hitting rule right here. Mud pumped in must exactly equal mud returned. If you calculate that you should get 0.12 barrels back per foot and you get more, the formation is kicking gas into your well. If you get less, your mud is leaking out into the rock. That math is literally your one and only early warning of a blowout.
Volume math also dictates well servicing. For instance, if you're using a wireline baler to clean out sand, the volume formula is the inside diameter squared times the length in inches times 0.0034. So for a 2-inch diameter tool that is 20 feet long, you only pull about 3.3 gallons of debris per trip. The math proves that baling is agonizingly slow, which forces crews to plan these cleanout trips very, very carefully.
Finally, Section 4, Torque, Output, and Production, Mechanics in Motion.
Once a well is actually drilled, the continuous dynamic forces of fluid rotation, artificial lift, and pneumatic power completely take over. First up is the slip velocity principle. Basic physics tells us that debris will sink through a fluid at a specific rate. If the mud is moving upwards slower than that sinking rate, which we call the slip velocity, the debris settles out. This is exactly how hole cleaning junk baskets work. They deliberately create a wide spot in the drill string where mud velocity drops, allowing heavy junk to just fall harmlessly out of the flow and into the basket.
Now once we strike oil, we use pumping units, or pump jacks, to get it out of the ground. Production sizing is basically an algebra equation. It combines stroke length, strokes per minute, the pump's plunger area, and overall efficiency, all multiplied by 1,440 minutes in a day to give you barrels per day. You don't have to guess the output. You can calculate it down to the exact barrel based on these exact mechanical settings.
And just looking at the stroke length variable, these units typically range from 40 to 192 inches. The math reveals a vital safety and efficiency secret here. Simply doubling the stroke length will perfectly double your production without having to speed the unit up at all. This keeps those massive steel counterweights safely ticking along at a nice, steady 6 to 12 strokes per minute.
Wrapping up our mechanical forces, we have to look at the rig floor's power source. Rigs use a 120 psi compressed air ring main to power hoists and tools, rather than electricity. Why? Well, as the quote says, an air motor physically cannot spark. This merges the physics of compressed gas with the harsh reality of safety. Just one rogue electrical spark near an invisible gas leak on the floor is all it takes to lose the entire rig. Which leaves us with this final thought for today's explainer. When you look at an oil rig holding back 15,000 psi of explosive pressure, suspending 1,000,000 pounds of iron over a hole in the ground, what are you really trusting? The massive steel you can see with your own eyes, or the uncompromising invisible math that dictates exactly how that steel behaves? The equations don't bend, and they don't break, and that is exactly why they keep the crew alive.